In southern France, stretching across the rugged Tarn River Valley, an engineering masterpiece called the Millau Viaduct was built, setting the record for the tallest bridge in the world at a height of 343 meters. To easily visualize the scale of the main subject in today's video, if you place the entire Eiffel Tower of Paris at the bottom of this valley, its tip would still be lower than the top of the bridge's pylon. But for the engineering team, the number 343 meters was just the surface of a massive mechanical problem. What truly worried them was not just the risky, hollow geological foundation below, or the hurricane-force winds gusting up to 155 kilometers per hour, but also thermal expansion, an invisible force always waiting to tear apart this 36,000-ton steel structure. How do you push tens of thousands of tons of steel, sliding suspended in midair, and firmly anchor this entire giant pylon system when even the bedrock beneath the foundation is full of underground caves and highly unstable? We will explore this together in today's video. Before we begin, don't forget to like and share this video. Thank you very much, and now let's get started right away. For decades, the vital A75 highway connecting Paris to the Spanish border was always completely interrupted when approaching the town of Millau. Here, the terrain is divided by a giant rift, the Tarn River Valley. Millions of vehicles traveling at high speeds were forced to brake hard, driving down an old winding national road, crawling to the bottom of the valley to pass through the center of town, and then having to crawl back up the slope to reach the plateau on the other side. During peak months, this difference in traffic capacity and the steep terrain turned Millau into the worst traffic jam black spot in Europe, with gridlock traffic extending for dozens of kilometers. To completely solve this physical bottleneck, widening the mountain pass or digging a tunnel through the valley was entirely impossible due to the massive elevation difference. The only option? Draw a straight line cutting through the air, directly connecting the two edges of the plateau. This decision dictated the mechanical design of the project. A continuous bridge deck had to cross a distance of 2,460 meters, and due to the depth of the valley floor, the entire bridge deck had to be suspended at a height of 270 meters above the ground. However, to keep this massive structure standing firm in midair, the first and most decisive barrier actually lay deep underground. Practically speaking, the ground at the Tarn Valley completely failed to meet the technical standards for load bearing. Beneath the surface layer of the valley is a karst geological structure. This is a fractured limestone foundation filled with underground fissures and hollow cave systems caused by water erosion over millions of years. From a mechanical perspective, this is extremely risky. If you place a 245-meter tall concrete pylon carrying tens of thousands of tons of steel onto hollow ground, differential settlement will occur immediately. The massive vertical compressive force would collapse the underground caves below, leading to the concrete structure above tilting and completely fracturing. You cannot build a superstructure without a solid foundation. To overcome this, engineers had to completely remove this fractured rock layer from the load-bearing equation. The chosen solution was a system of ultra-large diameter deep shaft foundations. They mobilized heavy-duty drilling rigs, digging holes up to 15 meters deep, piercing through the entire hollow limestone area until hitting the solid bedrock. Immediately, massive structural steel cages were lowered into the drill holes. Thousands of cubic meters of high-strength concrete were pumped directly into the ground, cast into permanent deep shafts. Each main bridge pylon is placed on a foundation of 4 such giant concrete shafts, each with a diameter of up to 5 meters. Next, to distribute the maximum compressive force transmitted from the main pylon body down to these 4 underground shafts, engineers cast a monolithic reinforced concrete pile cap. This pile cap has a thickness of 3 to 5 meters, locking the entire underground system together. This structure creates a perfect base, transmitting the massive weight of the bridge through the weak geological layer, directly into the hard rock core of the Earth. As soon as the underground foundation system reached sufficient mechanical load-bearing capacity, engineers immediately began Phase 2, building the system of 7 main pylons. First, they proceeded to weave thousands of tons of high-strength rebar into giant steel cages, firmly anchored and reaching straight up from the pile cap. After the steel cage was shaped, concrete was pumped in to completely encase the core structure. However, to continuously raise this structural block to a record height of 245 meters, the traditional formwork method was completely impossible. Here, the engineers were forced to use a special mechanical system, jump forming technology. The construction process was operated in a strict mechanical loop. Rebar was woven and extended upwards, then high-strength concrete was poured directly into the mold. As soon as this batch of concrete set and reached sufficient load-bearing strength, a hydraulic jack system would automatically lift the entire formwork block and scaffolding, weighing tens of tons, sliding it up another 4 meters to prepare for the next pour. Notably, this mold system was not fixed at all. It was designed with smart joints to continuously and automatically shrink the cross-section of the pylon body as it reached higher, a mandatory solution to optimize aerodynamic drag. Just like that, the loop of weaving steel, pouring concrete, jacking the formwork took place continuously day and night until all 7 main pylons were completed and proudly stood in the middle of the valley. While these 7 pylons were being cast at the construction site, hundreds of kilometers away, the skeleton of the project was also being urgently manufactured. At metallurgical mechanical complexes, 36,000 tons of steel plates were being cut by plasma, bent, and automatically welded to create giant steel box girders. Their cross-section is not square, but features an airfoil design to slice through the valley winds. Thousands of these precast steel modules were then transported by super heavy transport convoys, gathered at the 2 bridge abutments on the plateau, and welded together into 2 continuous steel halves. And this is when the most brutal mechanical problem of the entire project appeared. How do you bring this massive block of steel across space and place it on top of the bridge pylons? Here, the engineers decided to use the incremental launching method, progressively pushing the entire bridge deck from both edges of the cliff. The engineers turned the 2 staging areas at both ends of the valley into giant pushing systems. The girder modules, after being welded together, would be pushed by a heavy-duty hydraulic jack system, sliding along the support pillars. After pushing a certain distance, they would weld a new steel module to the back, and then push again. Like this, the 2 halves of the bridge gradually extended out from the cliff edge, sliding on top of the concrete pylons to head straight into the middle of the valley. At this point, if you frequently follow high-speed railway viaduct projects, you might ask, why didn't the engineers at Millau use giant launching gantries to crane each girder span onto the pylons as usual? The answer lies in the limits of physics. First, distance. Railway launching gantries are only designed to cross a span of 30 to 50 meters. Meanwhile, the distance between the Millau pylons is up to 342 meters. Any crane attempting to extend its arm across an empty space longer than 300 meters would snap under its own weight before it could even place the girder down. Second, wind force. At a height of 270 meters, hurricane-force winds with speeds of 150 kilometers per hour would easily overturn any machine trying to suspend a structural block in midair. Returning to the longitudinal launching method. To eliminate the risk of gravity due to the extreme span distance, engineers proceeded to erect temporary bents, cutting the suspended sliding distance in half to just 171 meters. Along with that, at the front of each girder, they installed curved launching noses, acting as automatic levers to lift the steel smoothly onto the supports. Even more boldly, the two leading pylons were already built and launched together with the deck, using their own stay cables to pull and prevent the front end from sagging into the valley. Thanks to this, the two halves slid and met in the middle of the valley. But welding had to wait until midnight. Only when the temperature dropped to its lowest and the steel froze completely did lasers align the gap to the millimeter, allowing welders to lock the final joint tight. The two steel girder halves were officially merged. Now it was time to erect the remaining 5 700-ton pylons. To avoid extreme winds, these towers were transported flat along the deck. At the destination, the base locked into a giant mechanical hinge. Then, hydraulic jacks pushed the 700-ton steel block, pivoting at 90 degrees upright into the sky. Finally, 154 bundles of stay cables were heavily tensioned. The suspended weight of the deck was transformed into vertical compressive force, discharging deep into the earth. The temporary bents were dismantled, and the 2,460-meter steel strip officially stood on its own midair. On December 16, 2004, the Millau Viaduct officially opened, completely eliminating Europe's worst traffic black spot. The journey across the valley dropped from hours down to just 2 minutes. 343 meters tall, weighing as much as 5 Eiffel Towers, Millau is the ultimate proof of mechanical engineering defeating gravity. Most impressive was the engineers' strict discipline, patiently waiting until midnight to merge the deck and neutralize thermal expansion. If you love engineering, check out the Chenab Railway Bridge video linked right in the description. And you? Which construction phase impressed you the most? Please leave a comment below. Don't forget to hit like, subscribe, and turn on notifications. See you next time.